Power in AC circuits. This is an interesting discussion because what we have learned up to this point in the electrical world from first level was that the term power was really the only type of watts or energy transfer that we were going to see. We only dealt with resistors, and because of that, we had in-phase circuits, and the in-phase relationship meant that with resistive loads, we had watts. Now, this was energy which was converted from electrical form to another form and was lost from the circuit. It was in the form of heat, motion, or light. So in a typical resistive circuit, even if it was AC, we have the voltage and the current in phase with one another. And what that meant was that when the volts and the amps were at their highest value, we would get a value of watts being produced. So in phase meant watts were being produced, watts being consumed, or watts lost to the circuit, and they were always in this positive sort of hump form, kind of odd. If you were to do the calculation, a positive current times a positive voltage at their peak value, you would get the peak value of watts. If you were to take these two values at their peak, a negative peak value and a negative peak value, a negative times a negative equals a positive. And so the value of watts is always a positive indicator, and it's always with resistive circuits. So the in-phase resistive component in an AC circuit will always consume watts, and those watts will be lost to the circuit in the form of either heat or motion or light. Now, this is a little bit different when we start getting into out-of-phase relationships. In an AC circuit, due to these out-of-phase relationships, energy will be both stored and released inside the circuit. And this transfer of energy is called reactive power. And the interesting thing about this type of power in an AC circuit is that it's not lost to the circuit. It's stored in the circuit, and then it's released back to the circuit. So let's take a look at the first out-of-phase component that we have. And the first out-of-phase component we have is an inductor. And remember, an inductor will oppose a change in current rate, while a capacitor will oppose a change in voltage potential. So they're both opposing something within the circuit. So let's look at an inductor. So here's a purely inductive AC circuit. In a purely inductive AC circuit, we know that the voltage and the current will be out of phase with one another. And the degree of which they are out of phase is exactly 90 degrees. So that means that the current will reach its peak 90 degrees after the voltage has reached its peak. And the other term that goes along with a purely inductive AC circuit would be that the current here lags the voltage here. So remember, this vertical line is actually moving left to right. And whichever peak value it hits first, that is the leading component. So that means the voltage peak happens first, and then the current peak happens second. So the current lags the voltage. When we start looking at power with a purely inductive circuit, we are looking at the peak value of voltage, and at that same time, what is the peak value of current? And then we're looking at peak value of voltage or current and peak and value of voltage at the same time. So let's take a look at where we get these powers occurring. So at this point, we have a negative current and a positive voltage. And when we multiply a positive and a negative, what we get is a negative number, right? A positive multiplied by a negative gives you a negative value. Below this graph horizontal, the representation of this green line means that the circuit or the inductor is releasing energy into the AC circuit. It's releasing energy in through that counter EMF. As the current value is dropping, it is increasing its counter EMF and releasing energy into the circuit. On the top side here, Here's the highest current value and the highest voltage value that happen at the same period of time. If we take a positive and a positive and we multiply them together, we get a positive value of power. Now, this power is being stored inside the inductor in the form of counter EMF, electromagnetic bonds. Now, this graph continues to oscillate, positive and negative, positive and negative. So what that means is that in an inductor, that power will actually be stored, or sorry, rather released in the bottom into the circuit, but then it's going to start storing energy in the positive, and then it's going to start releasing energy and storing energy and releasing energy. And that's why we get an inductive kick on DC circuits, because we can store energy in an inductor. In an AC circuit, we're storing and releasing into the circuit 60 times a second. So storing energy, releasing energy. The top is storing, and it looks like it's happening between 90 and 180. So between 90 and 180, we are storing energy. We are releasing between 0 and 90 degrees. So keep those numbers in mind. Releasing 0 to 90 and storing 90 to 180. Well, let's compare that to a purely capacitive circuit. Now remember, a purely capacitive circuit is one that opposes a change in voltage, and what that has an effect on is the current and the voltage being out of phase. And in this circuit, we always say that the current will lead the voltage. So the current happens first. It reaches its peak value before the voltage reaches its peak value. And so in a purely capacitive AC circuit, the current will lead the voltage. Let's take a look at what happens with the power values in the same way that we did with the inductor. So now what we have is a reverse hump. So this kind of a little bit different. It looks like we have the highest current and the highest voltage at about 45 degrees. And a positive times a positive gives me a positive value of power. Down here, we have a negative and a positive. A positive times a negative gives me a negative value of power. And so in this scenario, what we have is electrostatic charges being stored. And again, we're storing energy in the capacitor from 0 to 190. And then we're releasing that energy, again, between 90 and 180. So what I want you to consider is the difference of time periods between these two. We have storing and we have releasing. Remember, with the inductor, when were we storing energy? We were storing energy in an inductor between the 90 and the 180 degrees. So in an inductor, we actually had storing. It's exactly the opposite of a capacitor. Now, what about in the inductor, when were we releasing? We were releasing energy between 0 and 90. Exactly the opposite of a capacitor. And so like most things in the electrical world, we have two components that do exactly the opposite or have the opposite effect when placed into an AC circuit. Now, this concept of energy being stored and released inside an AC circuit leads us to combine values of power and leads us to the terminology that we use in electrical to describe power, which is true power, the item that you are used to most often from first level, which is represented with a P in an electrical formula and measured in watts, which is referred to as true, active, real, or effective. And this is the power that's actually accomplishing work. We're actually doing something. We're moving an object. We're producing light. We are creating heat. And you'll notice our analogy here is the actual beer in the pint glass. It looks like a A beautiful pint of beer. I could really go for a pint of beer. But after this presentation, this here, this is referred to as reactive power. And reactive power is represented with a Q in electrical equations, and it's measured in VARs. VARs are volt amp reactive. VARs. And that's referred to as quadrature power or wattless power. And so you see that it is identifying the top portion, which is the head of that tasty, cold, clean, palate cleansing pint of beer. But the head or the foam doesn't really contribute to the nice, warm, fuzzy feelings you get after drinking such a beverage. Instead, it's simply a product of having poured this tasty liquid into the pint glass. The reactive power itself does not contribute anything to the experience, although visually it looks quite appealing. And I want you to keep that in mind, not the beer, but the actual electrical equivalency. The reactive power is wattless, as in it's not really contributing much to the circuit. What's interesting, though, is that the entire combined values of these two is important because the amount of energy that is being stored and released still has to be accounted for. And so we account for that with another third form of power, and that's called apparent power. It's represented with an S in electrical formulas, and it's measured in VA, volt amps. This is the total amount of power that this particular AC circuit requires. Now remember all of the Pythagoras and trigonometry that we did in the past, that is not lost on us. That's actually going to be used with this calculation because VA is not merely a sum of the VARs and the watts. No, it can't be a sum because remember VARs is from out of phase components. They operate at different phase angles and they happen at different times than true power, which is energy that is lost from the circuit. And so the process that we go through to calculate this is our standard right angle triangle. Apparent power, measured in VA, is the hypotenuse of our triangle. The vertical is referred to as the reactive power, that's Q, measured in VARs. And the horizontal is always active or true power, measured in watts. This triangle is very standard in its relationships in that the hypotenuse will always be the total. The horizontal will always be the in-phase component. And the vertical will always be the out-of-phase component, always, every single time. So this orientation becomes very standard. The angle in between is known as the power factor. And that's the ratio of actual watt power in comparison to the total required apparent power. So this angle here between the horizontal and the hypotenuse will have significance going forward and will be used time and time again. That brings us to the end of our presentation on AC power.